Welcome to the PIBBSS Symposium 2025. I am excited to host Paul Rapoport, or Lorxus as he is also called, for assistance games for unclear reward functions. You can leave, I think you can use the Q&A option to put questions. Paul prefers questions at the end, so probably around the 45-minute mark, we'll open for questions. There's also going to be breakout rooms after that, which you can join to do an open discussion. And feel free to take it away, Paul. And
Great,
let's
thank you.
give him a little bit of a
Get
hand.
started. All right. So, as described, my name is Paul Rapoport, also known as Lorxus. And this summer for PIBBSS, I worked on a generalization of cooperative inverse reinforcement learning or assistance games, relatively similar concepts, for principles which have unclear reward functions, CIRL, model of some variety of imperfect alignment to a principle. I'll get a little bit more into it later. Hi, Antoine. I'll get a little bit more into it later, but briefly, we have some variety of multi-agent POMDP, partially observable Markov decision process, set up with a principal who knows some ground truth reward function, for sure, like knows it for a fact, and maybe can't act, and an agent, in some sense subordinate to the principal, who doesn't know this reward function, who can always act, and who has the same exact reward signal. And the same reward signal is how we model this imperfect alignment, the same reward signal, lack of knowledge of reward function. So for some principled ramifications for AI safety, it tells us a little bit about how we might best use weakly agentic AI as some fairly safe force multiplier, and also what might go wrong even if we have a solid solution to AI alignment that just fell out of the sky into our laps. What could still go wrong? That said, in the classical CIRL and assistance game setup, there's this assumption that the human, the principal, knows the reward function, knows exactly what they want, knows what's best for a fact. I claim this is unphysical, I drop it. I term these equivocal principles, who probably have good priors about what the ground truth reward function is, and divide these up between ones that can learn the reward function pretty quickly and ones that can't. So for the simple case, the reward parameter is unknown, but can be feasibly learned, unlike in classical CIRL, where principal and agent have perfect vision of the whole world state. The reward parameter, the reward function is stationary, completely fixed over time. The reward parameter is known to the principal for a fact, but not the agent. The reward signal, perfectly clear. And we have this nice little apprenticeship CIRL style assistance game for figuring out how best to get the agent to learn the reward function from the principal. For the simple case, you can actually do a fairly simple approach where you treat the reward function. You get the agent to treat the reward function as, sorry, you get the principal to treat the reward function as a multi-arm bandit. You have an initial phase before the ACIRL technique where the principal literally just learns the reward function, maybe by directly issuing commands to the agent as teleoperation or a Waldo. The more complex and interesting case is where the reward parameter is not just unknown at the start, but infeasible to learn perfectly and can only be feasibly learned up to bounded error. For that, again, we'll get into it a little bit later, but the quick version of the potential approach is that we calculate the STARC metric first, and that lets us get regret bounds that are linear in that linear between the ground truth reward parameter and the principal's operating guess or the agent's learned guess, and it's linear in this distance, in this error. Okay. There we go. So for a high-level overview of results, I combined three existing ideas: assistance games, partial observability, and this STARC metric on reward spaces. I explored what happens when we relax a major non-physical assumption of most existing work, total initial observability of the reward function, sketched out a quick solution to a simple case of assistance games, specified a few possible objective functions that we could use pretty well to measure how well our agent is doing, and did a little bit of fairly simple algebraic manipulation to get a simple regret bound for agents whose principals have actually misspecified the reward in terms of the STARC distance between the specified reward and the true reward. And that was a little bit of fairly straightforward algebraic manipulation, a little bit of measure theory flavored things, and a little bit of philosophical interpretation. Right. So I'm just going to put this whole slide up for a moment so people can have a look. And so that'll be in the recording, but it's mostly not going to be that important. But for the notation, at least, for the philosophical interpretation here, again, we have a principle or some human, which starts with some knowledge, maybe full knowledge, maybe incomplete knowledge of the reward function, and must convey it, but in some cases cannot act, or at least connotationally isn't as good at acting. And we have A, an agent or maybe a robot, which never starts off knowing the reward function and can always act. And again, connotationally is better at acting. The two of them share a reward signal. If a principal gets a payoff of 5, they both get a payoff of 5. There's also the point where a lot of papers in CIRL use H and R instead of P and A, but I don't think we should limit ourselves to the Centaur case where we have specifically a human and a robot. This should be fully general. This should work fully generally for agents. All of this stuff about approach. A lot of the time when I was thinking about this stuff, I thought of it in terms of a very literal apprentice of we have some old master who knows what to do, but is maybe going a little bit blind or little, doesn't have good motor control anymore, and an apprentice who doesn't quite know what to do, but is very quick, learns pretty well, good with their hands. It should work just as well for pairs of people as it should for human AI pairs, and maybe even AI pairs, where we have some sort of weird additional alignment strategy here. But that's less important. Anyway, a variety of domains and functions, assorted world states, action spaces, a transition function that brings us from state human action, robot action to a distribution over new states, a reward function that takes in a parameter, theta, and goes from state, action, action, parameter to distribution over the reals, which is a fixed function that accepts a parameter that might not be known. And this generalized reward parameter, which lets us fill in a little bit of additional state information. But that's the important thing that we're trying to learn here. When I put in any of these slides a colon before a lowercase version of a domain, that indicates a type signature of some kind. For another couple of things, another couple of little preliminaries, there's this concept of Boltzmann irrationality or Boltzmann rationality, where an agent might take the wrong or worse payoff action proportionally to the exponential of the negative regret. So something like you maybe take the wrong action e to the negative something times the loss of the time. So if that parameter is really, really big, you're almost perfect. And if your parameter is like 0, then you're taking the wrong action like a third of the time. Finally, for a little bit of nitpick, reward signal is the actual number of utils, number of dollars, number of whatever that you get as, hey, this is how well you did. Reward parameter is, this is the thing that tells you what the real function is. Reward function is something of a dummy that tells you this is how the world works. This is how it accepts the reward function or the reward parameter and the state and the actions and gives you what your payoff is. So helpfulness theory, which is something that I've been calling the overall field of CIRL and assistance games and everything to do with those. A major theme of the following papers of my own research is helpfulness in this strong and broad sense. How much harder is it for a principal to teach their agent or an agent to help their principal if they lack a communication channel, if they lack good feedback? What kinds of things might go wrong, even if this agent wants to help the principal? How does an agent help a principal who might not know for sure what the principal even wants? So for some quick past work in fundamentals, we have the concept of a Markov decision process, which is a model of decision-making under uncertainty. And for a lot of these, I've put brief paper references for where these things were first or best described or discovered or worked out in detail. But very briefly, we have a state space, an action space, and some kind of usually stochastic transition function that takes in a state and an action and spits out a new state and a reward. And our goal is to come up with some policy going from states to actions that optimizes something cumulative about rewards. Reinforcement learning that then gets built on top of this where we have a large class of assorted training techniques that rely on using that reward signal from the environment to update policy towards getting better rewards. And this lets you attempt to get good outcomes, even if you don't have a closed form expression or any sort of like complete information about what kinds of things get rewarded or why. Okay, but what about the part where maybe we don't see the entire world? This is what's called a partially observable Markov decision process, where now the agent doesn't actually get to see the entire world. Maybe they see only part of it. Maybe they have some kind of nice prior, and we have this observation space omega and a function that takes in the end state and the action and spits out some observation token omega, as well as a discount factor between 0 and 1. I like strictly between. Some people say maybe you are allowed to have 1. But the idea here is you want to reward things that get the answer quick. And it's just straight up a theorem that optimal decision making here depends entirely on the agent's belief state, the posterior distribution over the states in S as given by our function O. Similarly, we have inverse reinforcement learning, where now we have an agent looking at some variety of other agent moving around the world, doing things that maybe max out the reward function, maybe don't. They get to see what they do. They get to see what the states are, possibly, see what the actions are for sure. And the goal there is to learn the reward function. So RL agents are suitable for fully observable Markov decision processes. But if you have uncertainty about the environment, now we need inverse reinforcement learning. And there's this paradigm called demonstration by expert, where if the two agents are trying to cooperate, if the agent who already knows the reward function is trying to teach the one that doesn't, one thing you might do is literally just demonstrate what kinds of things get you good reward. That seems like a good possibility. Seems like a good tactic to try. But one thing we should take away from these two additional concepts is that the relaxation of full observability assumptions is a very common research motif, especially as far as trying to make this be more physical, be closer in contact with how the world really works, because we don't actually get to see the whole world, right? Anyway, now we get into some models of decision processes of agents interacting with each other or trying to help each other. We have decentralized MDPs, which are basically the same thing as a POMDP, except now we have more than one agent and they're all taking actions at the same time. And now the transition function and the reward to each of the assorted agents is given by the hidden state as before and all agents' actions. It seems relatively simple as an extension, but it's a meaningful extension. It's one we want to have and one we want to think about. And for a couple of related concepts, there are Markov and stochastic games, which are something like what happens if we have a game theory style game with some stochastic payoffs. And again, repeated games also with stochastic payoffs. Shapley 1953, surprisingly old, these things. Also, we have the idea of an assistance game. And now we're getting to the kind of thing that I was very sort of thing that's close to what I was working on. This is the foundational idea. This is the jumping off point for what I started thinking about. It's any setup at all where we have a principal and one or more agents where the principal knows the reward function. The agent or agents take action on the principal's behalf, and they're trying to benefit the principal somehow without knowing the reward function at the start. And all the players, principal, all the agents get the same reward signal. So it's a little bit off scope as to exactly why, but this lets us merge learning and control. This lets us have relevance-aware querying, where if we have some simple text channel or text-like channel, our agents will very likely, or in some cases provably, wait until it's relevant to ask questions instead of loading all the questions about what it is the principal wants right at the start. Similarly, plans which anticipate future feedback. If we know that we have some kind of communication channel and we know that we're mixing our control and our training phases, then generally our agents will wind up trying to preserve optionality, trying to put off making irreversible choices or taking irreversible actions whenever they can. But maybe it's not possible, and in those cases, they just do their best. This is notable, though, for not actually having a fixed decision algorithm, right? Assistance games are very broad. So now we start thinking about more uh, concrete ways you can see assistance games, like CIRL, where we have just two agents, where only the principal knows the reward function, both players get the same reward payoffs, and now we assume that principal and agent both use POMDPs. And the nice thing now is that we have a pretty good sense of how an agent can help a principal if the principal knows exactly what it wants and can teach the agent competently. And in particular, there's this thing called apprenticeship CIRL, where we have an explicit training phase where the principal teaches the agent using methods that are better than demonstration by expert, because you both want to show, I mean, philosophically, you want to both show what gets you good reward and also what gets you bad reward. Go towards this, go away from that. And then afterwards, there's a deployment phase where the agent keeps on taking actions on the principal's behalf. Maybe the principal also gets to work together with it, but the important thing is the agent takes actions now, mostly on its own, and might still continue a little bit of reinforcement learning. Okay, so let's shift gears for a moment to talk about this STARC pseudometric. We have this reward space, again, where we go from a state, a bunch of different agents' actions, and an ending state, and we map that to the reals. Starting state, bunch of actions of different agents, ending state, some kind of reward number. And in their paper, STARC, a general framework, Skulls et al. 2024, we assume that the state space and the action space are straight up finite, although I'm reasonably sure you could do this, extend this pretty straightforwardly to a continuous or at least compact case. And this is specifically a pseudometric on reward space. This is a way of giving something like distances between reward functions that you could have on this space. So what do you mean like reward function? Okay. Well, first off, it's not a single pseudometric. It's a way that you can compute distances between different reward functions if you can take some measurements and do some normalization sorts of things. And it's a pseudometric because sometimes we have distinct reward functions that have distance 0 between them. I claim we want this, right? We don't necessarily want to treat different reward functions as different always. We want this to happen. We want two different reward functions to be treated the same, have distance 0, if they rank every possible policy from states to actions identically. In particular, this happens when our two reward functions only differ by these three properties: S primary distribution, potential shaping, and positive linear scaling. And I'll do these back to front. Positive linear scaling, if one reward function is literally just 2 times a different one, then so what? These are the same. Potential shaping, if you get some kind of payoff just because you started in one state or just because you ended in a different one, we should still not care. And for the last one, if we see that, this one is a little bit thorny, but if we see that the two reward functions have the same distribution of rewards based on the state that you draw from the end of the transition function. Like we have our state, we have our actions, we have our transition function that pushes you through into an end state, and you pull from that. If they're the same based on that, then we should just treat these the same. So these three constraints, and again, they prove in this paper that these three constraints, these three properties, if they differ by these three properties, if they're the same up to those three properties, then they rank all policies from states to actions identically. So we should just give them distance 0. So this gives us the form of a canonicalization function that collapses a reward space into a bunch of equivalence classes. And even better, we can get pretty sharp. We can get sharp, not even pretty sharp, just straight up sharp, upper and lower bounds on regret based on whatever measurements we take. And as they bring up in the paper, and which is a little bit out of scope here, but as they bring up in the paper, you can just use the null policy to get your measurements, right? Suppose we pick the null policy, get some measurements based on that, calculate our canonicalization function, get our distances based on that one policy, because this works for whichever policy you want to pick. In particular, This is a direct improvement over previous pseudometrics or previous metrics for reward space like Epic and Dard. All right, so I said a bunch of words initially about what my results were. Let's look at them in a little bit more detail now that we've thought about what it is I did. First off, the explicit specification of how to solve a simple case of assistance games with equivocal principles. First thing is, if we know that our principal can learn the reward function pretty quickly, we can just do that. It's not ideal, given that there are a lot of benefits like relevance-aware querying and attempted preservation of option value for the version for assistance games where we combine control and learning. But we can settle for the apprenticeship version. And if we do, all we need to do is tack on initial discovery phase. I didn't quite work out the details for whether this would also work if we tacked on a similar discovery phase for the version where we mix control and learning, or where we mix learning and deployment. But it seems likely that would work just as well. I've also specified a few objective functions, which we'll get to in just a second. Myopic, worst case mismatch, real-time reward, Pareto, unambiguously desirable. And finally, as we might suspect from the previous slide, we can actually get a pretty straightforward regret bound, which is linear and STARC distance, just by rearranging some terms. We also straightforwardly get a credence-weighted sum, which extends pretty naturally to a credence-weighted measure integral. I mean, that bottom version looks like it should be an integral, but it's actually just a sum for the classic case because, again, there's only so many reward functions. Our state space and our action space are both finite. So I'll pause on that for just a moment. Okay. So now let's talk a little bit about the objective functions that I described. All of these are taken and adapted from CIRL et al. 2024, where the initial context was actually my prior research direction, or the research direction that I had or thought I had at the midpoint, where I thought I was going to work on reward functions that might be influenceable or might change over time. And in CIRL et al. 2024, they introduced these dynamic reward Markov decision processes, where now we've got these reward functions that might be allowed to change over time. And it details some problems that can happen if you choose your objective function poorly. They actually show that all of the objective functions they display in the paper are not suitable because you wind up with undue influence where your agent winds up soul hacking your principal. You wind up with agents that freeze up because they're not guaranteed to have anything that they do be not be worse than doing nothing at all. So they do nothing at all. And also in one case, computational intractability, where it's not even clear that the one objective function even exists. It isn't specified. And even if it did exist, it'd probably be intractable to compute. But anyway, the four that I adapted were the myopic one, where you pick the policy which yields the best immediate expected outcome according to the agent's best current understanding of the reward function. We have worst case mismatch, where the goal is then to pick the policy that does as best as possible if subjected to subsequent pessimal red teaming. So like you pick the action that you pick, the policy that you have should generate an action where if you were as wrong as possible about what the reward function really is, you still do okay. There's real-time reward, where you pick the policy that has the best expected outcomes overall, where at each time step, we base this on something like the agent's knowledge when making the choices at each step, and we time discount, of course, because we want to prioritize getting it fast. And the unambiguously desirable Pareto criterion, where we start by looking at all of the policies that always do better, never do worse than the null policy on any reward functions that haven't been ruled out. And of those, we can pick any of those that are not strictly dominated by another. That's the Pareto part, right? Unambiguously desirable is no matter what the real reward function is, does better than doing nothing. Pareto is of those, pick one that you couldn't just trivially do better with. So there are some possibilities for varying this up, switching this up along a few different axes. We could instead base this on what the actual ground truth is if we have access to that, sort of behind the scenes. We could base this on the agent's guess, like I have for the forms here. We could base this on the principal's guess and see how well the agent is doing based on what the principal thinks. We could base this on a single best guess at things, if it's the agent or the principal, or we could let them specify some kind of distribution of like, how likely do I think this reward function versus that reward function versus the other reward function is, and use some sort of cross entropy approach. Notably, though, some of these, especially UD Pareto, have way more interesting behaviors in our initially unknown setting than in the original setting that I took them from. Possibilities can get ruled out. In particular, UD Pareto was one of the ones that suffered in the original setting from sometimes the agent just freezes up because maybe nothing it can do is any better than doing nothing at all. Because there, maybe we have some particularly nasty reward function that could be in our reward space for any given policy we could pick, where if you get unlucky, you have your policy, you have your bad reward function, and that bad reward function is worse than doing nothing at all. So the thing to do is just freeze up and never do anything. This doesn't happen for my case because you can rule out some policies. You can rule out some reward functions. You learn enough, you know enough, and then you can say, great, I know that it's not the bad one. Here are a bunch of possible bad ones that it's not. So again, I'm just going to pause on this for a moment. There's a lot of math, but hopefully you believe me that all of the math that I've written here corresponds to all of the assorted text that I've written here in slightly more detail. This is the kind of thing that I tend to refer to as a half translation out of math. But I'll pause on this for a moment so that people can drink it in. But these are all just specifications of the different kinds of objective functions that I described in somewhat more mathematical terms, and then actual straight up mathematical notation. But again, for a little bit better description of these and motivation for these, you want to go to CIRL et al. 2024. Right. So what about those midpoint curiosities? You may remember, maybe you don't, that I had the suspicion that you would have a regret bound that was either constant somehow, or some kind of reasonable polynomial. Maybe it's linear, maybe it's log linear, maybe it's quadratic or something, based on some sort of meaningful distance on reward space. Or maybe to just be really bad, exponential or no bound at all, or something like that. But I think I mentioned at the time that my suspicion was that it would turn out to be the middle one, that there would be some reasonable function of some reasonable distance, and that would be a regret bound. Turns out I was right. How about that? It's linear in the STARC pseudometric on reward space. For another one, best practices for a principal that doesn't start off knowing the reward function, they were covered, like those got covered by the objective functions that I proposed here, but further work on that ended up being a little bit out of scope and would have required probably working with someone who is a lot better at empirics, a lot better at like fun biology style graphs. As I mentioned earlier, my direction changed actually like a couple of days after I gave that talk. Initially, I thought I was going to work on assistance games with a partially observable world and changing reward function. And that turned into instead a focus on imperfect starting knowledge of the reward function. And maybe we even still assume that we have a totally observable world and that we definitely assume that the reward function never changes. So no clear no-go theorem, but undue influence. And the equivalence between partially observable assistance schemes and DEC-POM DPs of some underspecified worst class ended up being a little bit beyond. So next steps. I plan to wrap up and polish my results into a short write-up, probably post somewhere, maybe even go for a preprint. There's some potential for further exploration of the objective functions I proposed here and some proofs about how well they do, right? We could maybe spend some time thinking about that. Something to do with the fact that credences of reward space, as I've specified here, are naturally over the reward space, But the STARC pseudometric gives us some quotient on reward space that more naturally carves it up into basically cones. Remember, if they're positive linearly scaled to each other, then they're the same reward function as far as the STARC pseudometric is concerned. So you wind up with something like cones here, surely. There's some potential for further exploration of best practices. Like I mentioned, it was a bit out of scope here. You could get some best practices, get some descriptive behavior, something to do with the possibility of aiming the agent at a distribution over reward functions, or maybe to do with cautious optimization. Both of those seemed pretty plausible. But ultimately, I'm less excited about this research direction than I was at the midpoint, unfortunately. The fact that we've got this very strong starting assumption for even some proxy of outer alignment still seems too strong to me. Reward signals are at best imperfectly read from principle and environment, and at worst, maybe whatever ML algorithm is just ignoring them somehow. It's not clear how they would, but we still have this proxy.
Paul, we cannot hear you again. I can try now. We cannot hear you.
How about now?
Yep.
Yeah.
Great. Sorry about that. Headset keeps turning itself off because it doesn't think I'm using it. It's wrong. Anyway, what was the last thing you heard me say?
It was like 15 seconds ago.
Was it about cautious optimization, or did you not catch that?
I think I didn't catch that.
Okay, so I'll start with the third bullet point again. So there's a potential of further exploration of best practices for and descriptive behavior of equivocal principles. So maybe we have this idea about aiming the agent at a distribution over reward functions rather than just a single one. Maybe we have this idea about cautious optimization where we try and aim it at a broad patch and try to get whatever our agent is doing to not rule out too many things. But overall, unfortunately, I'm less excited about this research direction than I was at the midpoint. First off, we've got this really strong assumption for a proxy of outer alignment. Our reward signals are imperfectly read from the principle and environment at best, right? But like as it stands, the assumption is basically that the agent is reading the principle's mind. For another problem, there are all of these different overlapping, really strong total observability or like perfect stationariness assumptions. We assume that a reward function is perfectly stationary, except that they shouldn't be. They change over time, can be influenced. We assume that the world is totally observable, except it's not. Parts of the world are hidden. We had assumed that our reward functions were perfectly known at the start, except they shouldn't be, as I've described. Overall, seems like some very strong assumptions that are all orthogonal to each other and would probably need to all be relaxed to make this research direction work properly. Worst of all, the CIRL approach doesn't really look to handle core questions of agency, let alone ontology. Doesn't really tell us how to build an align agent, doesn't even tell us how to recognize one. That said, a lot of parts of this were pretty cool. I found things about the pseudometric pretty interesting. Totally happy to talk about it anyway. I might even wind up working on it a little bit in future. How am I doing? I'm doing great on time. So thank you for coming to my presentation. I got through it a bit quicker than I expected. Half an hour for Q&A should start now.
Thanks very much, Paul. How's the noise? Can you hear me okay? There's
Yeah,
a lot of construction in the background. I hope that's not
coming through. Unfortunately, there's a lot of what sounds like static, but I assume it's construction.
It is construction. Thank you very much. Let's give Paul an applause.
Thank you.
And we can do Q&A now. You can use the Q&A function. I don't think anyone's put in any questions yet. You can also raise hand directly if you'd like to since no one's put in any questions, using the Q&A feature, and we can call on you.
Yep, sounds good. Let me start back sharing again, except This way I don't have to. This way I can actually see the screen. Otherwise, a little bit inconvenient. Oh, something in
Yeah,
the
I think
chat.
there
Wonderful.
may not be questions. Keen has left, and we have Abhinav,
Oh, no.
Sahil, myself, and you here.
Alas. All right, go for it.
I think one of the audience members is talking, Paul. You'll have to repeat the question because it's not audible to us.
Yeah. So Antoine, who is here in person, wants to ask a question. But what's the question?
So what do you think is currently the least bad or the most promising direction to address that question or that problem?
So the question from Antoine was, if I'm so down on the CIRL direction for trying to handle AI alignment or AI safety, what do I think does have the sort of sauce here? What do I think does have a shot at answering these questions? Is that right? Okay, yeah. I am not totally sure. I am going to be spending a fair amount of time working on the eliciting latent knowledge problem. And that seems to have some shot at answering some questions about how do you recognize an aligned agent, because those will probably be the ones that don't lie to you so much. But on the other hand, both a result from Andis Dragons, I think last year, and also a pretty straightforward philosophical argument of you probably can't get one over on something smarter than you, make me a little bit worried about whether or not elk is possible in principle or whether it's just doomed from the start. For another possibility, everything to do with John Wentworth's sort of atoms to agent style agenda seems also promising to me for different reasons, but I'm not quite sure whether or not that's going to pan out either. It seems in very early stages at best. Let's see. What else do I think there is? I'm not quite sure what else I would think there is, but if I had to pick a third thing, it'd be something like maybe we do something like this CIRL thing, except now we represent the fact that like our agent or even our principal doesn't really have a good handle on the reward function, or might not start with a good handle on it with like creedal sets or infrabase somehow. And then we'd have some additional control over to what extent our reward function is well understood, something like that, how well it's understood, or what kinds of safety properties it'll have. But like, I don't know, maybe you wind up with better guarantees on training then. Although unfortunately, I'm ultimately not too sure. Does that answer your question? All right, thank you.